Going to the next talk, we are going to have, you were expecting for Millie, but Millie is there, just there, all right? So if you want to, to talk to Millie afterwards. But here we have Thomas. Thomas was actually the person responsible for the work that Millie would be presenting. So he's going to be talking to us about Raman studies in triple and double wall carbon nanotube. So just go ahead.
Okay, can you hear me? Yeah. Okay, wonderful. So my name is Thomas. I'm a PhD student from Millie and Professor Cornelius Nisch in Hamburg. And the last years I studied double and triple wall carbon nanotubes in Hamburg, and Cambridge, and in Munich. And so we also cooperate with Professor Kim and Muramatsu in Japan and Korea. So the topic is about the Raman studies on double and triple wall carbon nanotubes. And just 1 second. Okay. And here you see the outline. So in the beginning, I'm going to talk about the motivation and about the growth method. Then I switch to the bundled double wall carbon nanotubes. So we studied the RBMs and the G' band. Afterwards, I'm going to talk about the individual double wall carbon nanotubes, and afterwards triple wall carbon nanotubes. We will talk about mainly the radial breathing modes in the beginning, and then we switch to the deep G- band and G' band from individual species and triple wall carbon nanotubes. Okay, so let's start with the motivation and the growth method. Okay, so as we just heard, that few walled carbon nanotubes are very interesting because they have a higher mechanical stability. They are thermal, show better thermal stability in comparison to single walled carbon nanotubes. They have an exciting electrical, thermal, and mechanical optical properties, and also the properties of having more concentric tubes inside each other is even more complex. But it's more interesting for many applications. For example, sensors, probes, field effect transistors, and many more. So we try to get here some more information about the growth method by doing Raman spectroscopy measurements, and to have more details about the growth method, to maybe later have grow nanotubes with an equal nanotube diameters, or just with a single flavored double or triple wall carbon nanotubes. And also we studied the few walled carbon nanotubes to get a better understanding of the intertube interactions in these systems. Okay. Okay. So what does these intertube interactions mean? So we have several influences to these systems. For example, the environmental influences. So the double wall carbon nanotubes can be in liquid, in gases, in solids. So the Raman mode shifts, also the properties changes, and also the nanotubes can be on different substrates, and the substrate interacts with the nanotubes, or we apply pressure on the carbon nanotubes, and the modes shift, etc. And or we change the temperature. We also can study suspended double wall or suspended tubes, and or we have the case of a bundle where the outer tubes interact with each other very strong. But the topic of this talk is mainly about the different kinds of interactions between double and triple wall carbon nanotubes. So, for example, we will see that the wall-to-wall distance is has a strong impact to the interaction between the tubes, also the diameter, so with the same wall-to-wall distance, but with different diameters. Or we will see that the high curvature, so if when the inner tube diameter is very small, we see not only intertube interactions, but also intra-tube interactions. Then we will see that the growth method is very important for the intertube interactions. So it's a difference between the P-pod growth method, or you have the CVD growth method, where on the one side you have the host tube and then you produce the inner tube later, and with the CVD method you directly grow two tubes on the same time. Then another impact to the interaction is, of course, the number of concentric walls in a system. Also, there is a mechanical coupling between these RBM modes for certain double-wall carbon tubes or triple-wall carbon tubes. We will talk about metallicity dependent and chirality dependent interactions, and also the flavors. They are also very important for interactions. So at first I will talk about the growth method to produce double-wall and triple-wall carbon tubes. So at first the double-wall carbon tubes was prepared by having arc discharge single-wall carbon tubes, and then later we put fullerenes inside and heat them up by different temperatures. So we grow these high-quality double-wall carbon tubes. And the triple-wall carbon tubes was a little bit different. So we had as a host material, it was diameter enlarged double-wall carbon tubes, and then later we put fullerenes also inside, heat them up, and we got this triple-walled structure. So by having both systems with the nearly same method for the inner tube, we can perfectly compare the different kinds of tubes, because the method was nearly the same for the inner tube. And what we did is we changed both the double and the triple-wall carbon tubes. So the annealing temperature we changed stepwise between 1,500 and 2,000 degrees. And so we studied all the Raman modes and saw differences and similarities. And it's good to study these two systems with the same method for the inner tubes to make some statements about the intertube interactions. Okay, here you see the Raman spectra of bundled triple-wall carbon tubes. You can see here the radial breathing modes are highly intense or well developed. Also the D band, the G, and very strong is also the G prime band. And here the upper spectrum on the bottom shows a spectrum of an individual triple-wall carbon tube, where we see that the triple-wall carbon tube was placed on a silicon substrate. So you also have the silicon peaks. And here you see the RBMs from the middle and from the inner tube, and also the G prime, the G band with having a G plus and a G minus peak, and a well-developed G prime band. So in this talk, we are just talking about three different modes. So at first, the very important radial breathing mode, and then we talk shortly about the G band and also the G prime band from individual tubes. So starting with the bundled samples. So just as a background, here Mr. Pfeiffer et al. Studied these experiments here on comparing single wall carbon nanotubes with double wall carbon nanotubes and what is different. So a single wall carbon nanotube shows here, you see the radial breathing mode window, shows a single peak structure for the 6.5 and 6.4 carbon nanotube. And in comparison to a double wall carbon nanotube, it's an even more complex system. So instead of having a single peak structure, you see these clusters of peaks. And one cluster, so here in this case you see two different inner tubes, and one cluster can be can have a width over up to 30 wave numbers, and one line width of an individual peak can as small as 0.35 wave numbers. So it's very tiny, which also tells us that the quality is very good and the phono lifetime is very long. And then we see that the shift is due to wall-to-wall distance changes in a wall-to-wall distance, as well as changes to other interaction differences. And what is also interesting is that the resonant windows are downshifted in energy in comparison to the single wall carbon nanotubes, and that on top of that, in one cluster, the peak also shifts down in energy by increasing the frequency. Okay, and another point is that each cluster of peaks start more or less with the relation 227 over the diameter, so which means all peaks are upshifted in comparison to this relation here. Okay, this was background. So now you see the measurements on bundled double wall carbon nanotubes. So at first you have the host material. You see here the radial breathing modes of the host carbon nanotubes with a certain diameter of around 1.3 to 1.6 nanometer. And then you see one peak from the, so here you see the radial breathing mode frequency range, and here the G' frequency range by around 2600. And then we put it the fullerenes inside, and we heated it up by 1500 degrees. And you see additional peaks here in the high frequency range for coming from the radial breathing modes from the inner tubes, and you see an additional peak from the G', which is also coming from the inner tubes. And so we grow very small additional inner tubes. And then we increase the temperature from 1500 to 2000 degrees, as mentioned before. And we see that the intensities on one side increase, as well as the frequency shifts to lower frequencies. So, which means that by increasing the temperature, the annealing temperature, the diameter of the inner tubes also starts to increase. And you see here very good that at 1500 the radial breathing modes are here over frequencies more than 300 wave numbers, and then later at 2000 degrees you see also that the host tubes start to be larger, so the diameter is going to be larger, which means that at temperatures over 2000 degrees you produce diameter enlarged double wall carbon nanotubes. And so we studied these radial breathing modes of the inner tubes in more detail, and as well we also studied the G' bands, and we saw that there exist many influences of the metallicity as well as from the diameter. And okay. Okay, so going to the next topic is we are going to talk about individual double wall carbon nanotubes. So this is also work there was a work done in 2010 by Villabando Baez. He found 13 individual p-pod derived double walled carbon nanotubes, and here it is very interesting that all individual double walled carbon nanotubes have the same flavor, and even the inner tubes are nearly the same. So it's a 9-1 and so 291 nanotube and 1165 nanotubes. And here is interesting that the inner tube from both chiralities have the same diameter of only 0.747 nanometer. And then just very recently, Lesov and Louis et al., they published 2 different publications about one CVD-grown double-walled carbon nanotube and 13 CVD-grown double-walled carbon nanotubes with 3 different flavors, and they, on top of that they used Raman spectroscopy. They also did Raman, the TEM diffraction pattern to characterize and to get information about the chiralities. And here it's the main difference between these 2 tubes, these double-walled carbon nanotubes, is that the inner tube diameter is much larger. So the inner tubes are here around 1.6 to 2.5 nanometer, which is larger than in comparison to the 0.7 nanometers. And also the measurement strategy was different. So here the double-walled carbon nanotubes are lying on a silicon substrate, and in this case of the CVD double-walled carbon nanotubes, they were free-hanging. So when we just focus on the radial breathing mode frequencies in comparison to the wall-to-wall distance, so in this plot you see the wall-to-wall distance versus the frequency upshift in relation to the 227 over the diameter, and you clearly see that there are differences between these tubes, so the p-pod derived tubes and the CVD double-walled carbon nanotubes. And here you see that the p-pod derived tubes are, the wall-to-wall distances are smaller than the interlayer distance of graphene, which is which is found to be 0.335 nanometers, in comparison to the wall-to-wall distances between the larger CVD double-walled carbon nanotubes. And this plot here perfectly shows that the interaction between the tubes are higher in the larger tubes in comparison to the smaller diameter tubes. Okay, and then now we go and see what is new about the individual triple-walled carbon nanotubes. So we see here the radial breathing modes of the inner of 5 individual triple-walled carbon nanotubes. So we found for 5 different tubes 3 possible flavors, 3 of 4 flavors. And so here you see the S at M double-walled carbon nanotubes. The inner tube is in semiconducting, and the host tube, so the middle tube, is a metallic one. And then 2 tubes with a semiconducting flavor. And the third flavor is a metallic inside of a semiconducting tube. And the wall-to-wall distances between these inner 2 tubes of a triple-walled carbon nanotube was found to be 0.31 to 0.329 nanometers. And this is in agreement with the p-pod derived double-walled carbon nanotubes. And because here the inner tubes are also grown with the p-pod method, then we did to say something about the outer tubes, which we could not detect with the Raman setup. So we did AFM measurements to check the height of the outer tube, and we saw that it is in the range where we expected it, around 0.95 nanometers. And we also, what we did is we changed the laser energy, so we get very nice results about, for example, the radial breathing mode windows. So here you see that the middle or the host radial breathing mode starts to increase the intensity by shifting the laser energy from the green laser to 2.1 electron volts, and here you see that that the inner tube just starts at 2.19 electron volts around this, starts to increase, and so we found that the resonant window of the inner tubes are around 0.5 electron volt. And now we can just put these findings into the just shown plot, and so we see here the wall-to-wall distance versus the frequency upshift, and we see that the triple wall carbon nanotubes are between, so for the inner semiconducting tubes, we see that they are between the p-pod double wall carbon nanotubes and the CVD double wall carbon nanotubes, and which also, when we go into detail, we can make many assumptions about the interaction between the tubes, depending on the flavor, depending on the metallicity, because we have 6,5, 6,4, and 5,4 semiconducting inner tube. And what is also very interesting is that the metallic inner tube inside of a semiconducting tube behaves differently, which also tells us when we studied the bundled double wall carbon nanotubes. So the metallic inner tubes can be seen as nearly isolated in these tubes, and it's very interesting. And then we can go, because we also, besides the radial breathing modes, we have other modes which are influenced by the intertube interactions. So one example is the G- band, and we see here from Talc et al. The work on single wall carbon nanotubes. So because the inner tubes of the double and triple wall carbon nanotubes are very, very small, the diameter, we have these two tubes. We are here in the corner of this plot, and we see that the single wall carbon nanotubes are placed here at this frequency range and the diameter, and then we can just include the results from the double wall carbon nanotubes from with the 6,5 flavor, or with the 6-fiber inner tube, and we see clearly that the wall-to-wall interaction increases, and we get a shift in frequency by changing the wall-to-wall distance, and then we additionally can include the results from these G- frequency results from the individual triple wall carbon nanotubes, and here all are semiconducting. So we see that the 6,5 nanotubes agree with the double wall carbon nanotubes. Also, they show the same shift, and also we can look at the 6,4 and the 5,4 frequencies, and it's very good relation to the theory and to the fit of the single wall carbon nanotubes. And here, so the last slide is about the G' band of an individual triple wall carbon nanotube. So in addition to the RBMs and the G-, we see that the G' band shows a triple peak structure, which tells us that the interaction between the tubes is very low, and that each tube contributes individual to the G' band. And so by changing the laser energy from 2.11 electron volt to 2.5 electron volt, we see that the shift the peaks also shift with the laser energy, which is expected, and also that the slopes are different for each tube because they have different dependencies on the coupling between the bands, and here we see that we have 3 different dispersions for each tube. So, for example, the inner tube have a slope from 98 times the laser energy, but the outer one has 150 times the laser energy. And so this plot tells us that the interaction is very weak, but also that there's no band coupling between the tubes, which is seen by graphene, for example, and that with this method or with this plot, we also can do an assumption that the outer tube could be semiconducting because it's more resonant in around 2.4, 2.5 electron volts, and when we have a close look to the Kataura plot, we can assume that the triple wall carbon nanotube has a 3 semiconducting flavor. Yes. So, as a conclusion, we showed that the bundled results are very useful to make some statements about the growth method, and that it is very helpful to study tendencies of the Raman features, but also we saw that it's pretty hard to say any real statements about the intertube interactions and other things. So the study on individual tubes is a study on individual nanotubes is required, and so to summarize the results from the individual species, we saw that it is that the intertube interactions are very different between the 2 different growth methods, and that that the nanotube diameter is has a strong impact to the nanotube properties, to the electronical and optical properties, and that double and triple wall carbon nanotubes are we compared double and triple wall carbon nanotubes with each other, and that also that the intertube interactions between the tubes has so many parameters, and so it's a very complex topic, and we need many more individual tubes to have a nice statistic, and the results also showed that the intertube interactions not only influence the radial breathing modes, but also the G- band, for example, and so thank you very much for your attention.
So if you have any questions, yes.
Hi, thank you very much for this very nice talk. I have a question about the strength of the interaction between the different tubes.
Yeah.
Did you compare with as-grown triple wall carbon nanotubes, for example, to see there is a difference between the interaction if you make the triple wall tubes from pipods, from double wall tubes, or if you work directly with as-grown triple wall carbon nanotubes?
No, we did not compare this, but we compared the results from with the double wall carbon nanotubes. They are as-grown and.
Any other questions? So if not, let us thank the speaker again.